Assalamualaikum and hi everyone. I'm Muhammad Akmal from Mechanical Precision Engineering under a supervision of Prof. Emeritus Dr. Matno bin Musa. I'll be presenting my FYP, which is Liquid Thermal Conditioning System. First of all, have you heard about temperate crops? Temperate crops are crops that are usually grown in seasonal country that have a suitable temperature of between 15 to 20 degrees Celsius. In a tropical region such as in Malaysia, it is grown at the hill slopes of mountains such as Cameron Highland and Kundasang Sabah. But now with the advancement of technology, we can grow temperate crops in a tropical climate region by controlling the environment temperature and also its humidity. It is proven that the temperate crops such as lettuce are successfully grown under a temperature of 15 to 20 degrees Celsius with the help of root zone cooling method. Root zone cooling method is a method of cooling the roots of the plant by using any kind of medium such as hydroponic solution to activate good bacteria to increase the absorption of nutrient from the roots. From a study, the control of root zone temperature is much easier and more economical than that of other environmental factors such as air temperature, and can be an effective solution to temperature stress. Thus, by creating a root zone temperature control system such as the LTCS system, we can use this approach to commercialize the temperate crops at a lower cost and meet the domestic market in Malaysia. In creating a hydroponic solution of a temperature profiles resembling a temperate region which is between 15 to 20 degrees Celsius, liquid thermal conditioning system is developed to cool down the hydroponic solution which later will be used for the temperate crops in the hydroponic system. By having a cool temperature hydroponic solution, high quality temperate crops such as lettuce, cabbage and berries can be produced even though at a tropical climate region. Therefore, the objective of this project is to develop system of liquid thermal conditioning system to cool down a hydroponic solution in response to the temperature around the crops by using a computational fluid dynamic simulation CFD. Other than that, this study also tried to find an optimum design for the cooling system by manipulating the shape and the dimension of the cooling tower. Initially, liquid thermal conditioning system was planned to be built by combining a refrigeration component to a hydroponic system and run an experimental work to observe the growth of the plant and study the effectiveness of the system. But due to the COVID-19, the work cannot be continued even though it is already at a large stage of fabrication. Thus, the study has changed its focus to computational fluid dynamic simulation on the model design that have been proposed before. In simulating the temperature distribution of the cooling tower, where the hydroponic solution flow through the PVC pipe while being cooled down by a cooled refrigerant 134A from the coil, both of the fluid temperature and velocity have to be well distributed to ensure the cooling of the hydroponic solution in the cooling pipe is at the optimum level, which will give the desired average temperature of the outlet. The first step of starting a CFD simulation, a model must be designed and drawn by using any kind of 3D drawing software. In my case, I'm using a SolidWorks 2020 as my platform to design and test a few of the model by manipulating the dimension and the characteristic to find the most optimum design to cool down the hydroponic solution. In this simulation study, there are 8 models that have been chosen to test their effectiveness in cooling the hydroponic solution by using a cooled refrigerant 134A. As you can see from the table, we have 4 models with 6.5 cm diameter PVC pipe, with 2 of them have 36 coil of copper hollow helical coil, while the other 2 of them have 20 coil, and each one of the model have the same number of coil are divided into 2, which is 1.588 cm and 0.952 cm of diameter evaporator coil. The other four models below have the same copper hollow helical coil but different size of inner diameter PVC pipe, which is 10 cm. Here are the example of the model in SolidWorks drawing. The cylinder-shaped PVC pipe are the PVC pipe where the water will be filled in that space, while the coil in the cylinder are the copper helical coil that will be filled with refrigerant 134A to cool down the hydroponic solution. Note that the refrigerant and the copper helical coil in the cooling tower act as an evaporator which will absorb the heat from the hydroponic solution in order to cool down the hydroponic solution. Lastly, all of the 8 models have been set with fixed variable, which is the height of all of the model are kept at 120 cm, thickness of the PVC wall are at 1 cm, and the thickness of the helical coil are 0.061 cm. This dimension of PVC pipe and helical coil are based on a real product that are currently available in the market. Now, we have reached the stage of computational fluid dynamic simulation of this project. So after we determine the design of the model, CFD model setup are needed to develop a CFD simulation using the SolidWorks flow simulation. So simplification of the actual problem are needed, which allow the analysis to be done with a reasonable effect. Few assumptions are made where both of the fluid, which is the refrigerant 134A and the hydroponic solution in the cooling tower and helical coil are incompressible. Flow and heat transfer occur in a steady state condition. For the general setting of all of the model, we will set the type of analysis as internal, type of fluid 1 as refrigerant 134A, fluid 2 as hydroponic solution or water, type of material 1 as copper, which is the helical coil, type of material 2 as PVC, which is the PVC pipe, and the initial condition of all the model are constant pressure and constant temperature. Other than that, the inlet of PVC pipe is at 30 degrees Celsius, the inlet of copper helical coil is at 10 degrees Celsius. Be noted that the hydroponic solution characteristics are as same as water fluid. This is because in any hydroponic system practices, a solution used are first being diluted by water before entering the hydroponic system. Thus, the difference in density and viscosity of water and hydroponic solution are very small and it is always considered as negligible. Other than all of those data mentioned earlier, there are other data input that are very important to be considered before running this CFD simulation. First, the initial temperature of the water are 30 degrees Celsius. The initial temperature of refrigerant 134A are 10 degrees Celsius. The mass flow rate of refrigerant 134A are 47.1236 kg per second. Mass flow rate of water are 5.1972 kg per second. Pressure of water are 1325 Pascal. The pressure of the refrigerant 134A are 416,176.47 Pascal. And finally, the wall condition is considered as adiabatic wall. From the result data obtained from the CFD simulation analysis that have been run on all those 8 models are shown in the table and also the graph. The model that have 10 cm diameter of PVC pipe, 0.952 cm diameter of helical coil, and number of coil of 20 achieve a maximum average temperature of water, which is 32.77 degrees Celsius, while the model that have 6.5 cm diameter of PVC pipe, 0.952 centimeter diameter of helical coil, and a number of coil of 36 achieve a minimum average temperature of 18.92 degrees Celsius. This shows that the range of temperature achieved by all the models tested are between 18.92 degrees Celsius and 32.77 degrees Celsius, which is 13.85 degrees Celsius in difference, which is very huge. Other than that, based on this result, it is shown that the most effective model are the model A1.2, which have a 6.5 centimeter diameter of PVC pipe, 0.952 centimeter diameter of helical coil, and number of coil of 36. Figure shows the distribution of refrigerant 134A and water in the cooling tower of both A1.4 and A1.2. The level of the temperature are shown in the form of temperature gradient. Based on the result shown, model A1.4, which have a 6.5 cm diameter PVC pipe, 0.952 cm diameter of helical coil, and number of coil of 20, achieve of 23.33 degrees Celsius, while for the model A1.2, as we mentioned earlier, it achieved 18.93 degrees Celsius. For the model A1.3, which have 6.5 cm diameter of PVC pipe, 1.588 cm diameter of helical coil, and number of coil of 20, achieve 29.1 degrees Celsius. While for the model A1.1, which have a 6.5 cm diameter PVC pipe, 1.588 cm diameter of helical coil, and a number of coil of 36, achieve 21.91 degrees Celsius. For model B1.4, which have 10 cm diameter PVC pipe, 0.952 diameter helical coil, and number of coil 20, have achieved 32.77 degrees Celsius. While for the model B1.2, which have 10 cm PVC pipe, 0.952 cm helical coil, and the number of coil of 36, achieve 31.67 degrees Celsius. And lastly, for model B1.3, which have a 10 cm inner diameter of PVC pipe, 1.588 cm of helical coil, and number of coil of 20, achieve 26.61 degrees Celsius. While for the model B1.1, which have a 10 cm PVC pipe, 1.588 helical coil, and number of coil of 36, has achieved 28.148 degrees Celsius. Video shown on the next slide is the flow trajectory of the CFD simulation on the model A1.2, the most efficient model among all of the 8 models that have been tested. So, from the data obtained, a 36 helical coil model with a diameter PVC of 6.5 cm and 0.952 diameter of helical coil are the most optimal model with an average temperature of 18.92 degrees Celsius, which is the model A1.2. Based on the result also, from the CFD analysis, it is shown that the LTCS system are able to cool down a hydroponic solution into a desirable temperature for temperate crops, which is between 15 to 20 degrees Celsius. This analysis helped the study of temperature distribution for the cooling of hydroponic solution in the LTCS system. However, further studies need to be performed to develop the liquid thermal conditioning system, where this system is built in the form of refrigeration plant with the evaporator coil inserted through a cooling tower and mechanically joined with other components such as compressor, condenser, and expansion valve, and test the system. The hydroponic solution temperature can be measured by installing thermocouples at various suitable locations in the cooling tower and the hydroponic tower. A controller also should be installed to manage the daily liquid temperature to remain within the 15 to 20 degrees Celsius, and the rate growth of the temperate plants can be observed and recorded as a control experiment. So that's all from me. Thank you very much for your attention.